Wheels are a useful tool for providing mobility to objects on continuous surfaces. However, they struggle with handling discontinuous environments, especially when encountering obstacles larger than the wheel radius. To address this difficulty, a new transformable wheel mechanism is needed. We propose a shape-morphing wheel with high-speed locomotion, driven by wheel driving torque. As driving velocity increases, the wheel changes its shape into a tri-spoke configuration. The shape-morphing wheel consists of two main parts, the spoke and the wheel body. Each spoke is equipped with a magnet and a torsion spring, which act as trade-off factors. These factors initiate different sequences for the wheel's performance. When speeding up to overcome obstacles, the driving motor torque tau and spring forces activate the unfolding spoke stage. As the wheel slows down, magnetic forces and its own weight activate the folding spoke stage. Due to these trade-off factors, robust wheel optimization is necessary. Note that a basic constraint is merged. The spokes must fold and unfold during the overcoming sequence. To achieve stable performance, we used the Taguchi method for optimization. For the method, 4 design parameters were considered. The first parameter is the spoke central angle theta c. Varying theta c affects performance height based on vertical velocity. The initial theta c levels are 72, 90, and 120 degrees. The second parameter is the weight ratio ρw. The weight ratio between the wheel body and spokes is critical for lifting the body. The weight ratio levels are 3, 4.3, and 5.6. Main wheel components are divided into 3 levels as the third and fourth parameters. The goal is to maximize Z acceleration within a stable driving, following the larger the better principle. User conditions are ground friction μ and driving velocity v. Each has 2 levels. In case of the ground friction coefficient μ affects the height and vertical velocity. The test bench includes a counterweight system for adjusting weight ratio. The wheel has Z direction freedom for performance evaluation. The orthogonal array for the first experiments is L_9, 3 to the power of 4. Visualizations of each design are shown above. As the combination of user cases, the experiments conducted 4 different cases per one design parameter combination. Based on the measured data, the average Z acceleration measures performance. Here are the results from the first 9 design combinations. Each experiment is conducted 3 times to ensure repeatability. The results of the L_9, 3 to the power of 4, orthogonal arrays are shown. Repeatability is confirmed with CV% ranging from 0.012% to 0.534%. The SN ratio graph indicates the optimal magnetic adsorption force and spring constant. These are set to 6.66 Nm per degree and 1.439 Newton, respectively, because of the wheel basic constraint. If the magnetic force decreases or spring constant increases, folding is deactivated. The design parameters for the second experiments are based on the first SN ratio graph. They include 2 levels of the central angle and 3 levels of the weight ratio. The orthogonal array for the second experiments is L_6, 2.3. Values below 90 degrees for the central angle violated the wheel folding constraint. That is the reason of the central angle levels. The second experiment results are shown. Repeatability is confirmed with CV% ranging from 0.007% to 0.117%. The second SN ratio graph shows a reversed slope compared to the first. This indicates optimal levels of 102.86 degrees for the central angle and 4.95 for the weight ratio. The initial wheel is shown as a red wheel, and the optimized wheel as a blue wheel. Compared to the initial wheel, the optimized wheel has decreased spoke central angle and magnetic adsorption force. However, the spring constant and weight ratio are increased. The standard deviation of Z acceleration improved by 51.4% at the comparative experiment. This indicates improved stability under various conditions in the optimized design.